Now that you've seen some of the details about how the refraction microtremor technique works technically, it's time to look at some examples of what we've been able to find, what we've been able to measure using this very quick and easy refraction microtremor field work and pretty quick and easy analysis too. Here's a couple of pictures from a city park in the San Fernando Valley of Los Angeles, where we did an initial refraction microtremor demonstration, and you can see that we just put our geophone spikes into the turf and lay out our cable. We have a straight line extending over about 300 meters, and that's really it. Very simple field procedure. About half hour of recording total, and then we can pick up. Here's an example from the quad, and we tend to just spike the geophones right into the turf. That works just fine. We do like to level our lower frequency geophones, but for the 8 Hertz geophones used here, we don't even have to do that. And this gets us shear velocity information going down underneath the quad, and we've done that. We've repeated that experiment several times. And one thing that's really quite spectacular about the refraction microtremor technique is that you don't need to get really good what are called geophone plants, or really good setting of the geophones into hard ground. That's certainly necessary for detailed seismic reflection work, and often to be able to see seismic refractions out to significant distances. But refraction microtremor isn't looking at the high frequencies that those techniques are looking for. Refraction microtremor is looking at frequencies of under 25 Hertz generally, and so even these what we call bad geophone plants, like on the right, spiking the geophone into the snow, or on the left, this is from a survey in the middle of the Truckee River on a gravel bar with the water running all around the survey. You can see these orange geophones that are kind of we wedged in between the cobbles in the on that gravel bar, and the white bags are the single channel recorders that we used. Could have also used our cables with swamp connectors as well. So the refraction microtremor technique is it's robust enough that you can record good data under these extremely trying field conditions, and thus it's very adaptable and very flexible for a huge variety of situations. Here's some geophones just shoved into the sand at the wet sand at Moss Beach, just south of San Francisco on the Pacific Ocean. So we were doing this kind of profiling across the end of a fault zone, just to examine differences in velocities between the fault zone itself and on either side of the fault zone. And here's a typical urban application. This is downtown Wellington about 10 years ago during the in New Zealand during the release of the second of the Lord of the Rings movies, and so you can see Gollum there reaching over the theater for that they did the initial release in for the ring of power there, and here's our single channel recorder with you can maybe barely see the orange geophone, and here's another one spiked into the turf in the park strip in the middle of a huge boulevard. Again, we don't have to avoid noise. We want as much traffic as possible. So refraction microtremor is an ideal technique for doing these kinds of surveys for velocity, for uh, earthquake hazards, for foundation studies, for urban planning. It works excellently right where you need it to work in the middle of the busiest cities. Here we are doing our transect through Los Angeles on the left, and that's on Terminal Island in Long Beach, California. And here we are in North Las Vegas, recording the all of the huge surface waves emitted as this train goes by, freight train. Freight trains are great sources of very low frequency microtremor energy, and we can pick those up with our refraction microtremor arrays. And the lower the frequency we can get, the deeper the velocity information we can get, because the lower the frequency, the longer the wavelength. And you can imagine a mile-long freight train is an excellent source of very powerful, very low frequency surface waves. Here's on the left surveying with a recorder every 20 meters by the county building in Clark County, which some of you from Las Vegas might recognize, on the north side of Las Vegas. Here's a recorder, the geophone spiked into an embankment with the recorder in the foil bag by the side of a traffic clogged 605 freeway in Los Angeles during our Los Angeles transect. So here's an early look at the results that we had just after a few years of refraction microtremor surveying. We had at that time found some very, very low velocities of VS30 of only 100 meters per second in a drained swamp in Wellington, New Zealand. And then on the high side, the University of Texas El Paso campus in Texas is built in an old limestone quarry, and we had a VS30 of 1100 there. Have had some similarly high velocities measured in Nevada, again in limestone terrains in southern Nevada, and you can generally see these measurements are arranged and named, but they're arranged in rough order of the VS30, the 30-meter average shear velocity. And there's also some comparisons here against the results of other techniques, and the comparisons are generally very, very good. All right, so given the ease of this technique, it was incumbent upon us to really do some exploration and figure out, well, how does shallow shear velocity really change over some distance? There's assessing shallow shear velocity used to be so expensive, with drill holes and cross-hole tests, costing $10,000 for each point. Now we can do academically or commercially. We can do refraction microtremor measurements at a very small fraction of the cost. It would be 1 to 5% of the cost of other techniques. So we began with a first large-scale test right here in Reno, where we surveyed along the Truckee River, the bike path, and certain of the roads that are running along the river. So we essentially did a 15-element refraction microtremor array centered on each of these green dots that follow the river through Reno here. The university's up here. This is red line is Virginia Street. There's a little piece of the McCarran Ring Road, Interstate 80 going from left to right, and I-580 now, or US 395 going up and down north to south across the area. So we span the valley with this, the central part of the valley anyway, with this this transect of refraction microtremor measurements. Now, so plotted here are the 30-meter depth average shear velocities from west to east, and it was no surprise that the generally lowest velocities were on the right side here, in the right half, at the the drain swamp of the Truckee Meadows, as it's known. Through downtown here, on the left half, the velocity is a little bit higher. The NEHRP hazard classes, National Earthquake Hazard Reduction Program, is a program that develops standards and classifications for the International Building Code. So the NEHRP classes are referred to in the building code, and B is soft rock. Okay, that's above this this teal line here, and above the pink line, between the pink and teal, is the stiff soil NEHRP C class, which is not very hazardous. The more hazardous NEHRP D class is below. Okay, so most of the Reno Basin turned out to be by our measurement in the NEHRP C class, whereas the default in the code, if you don't measure it, you have to assume NEHRP D, and there's relatively few places that are NEHRP D. One surprise, over here on the west side of west of downtown, west of Idlewild Park, actually near West McCarran and the river, that's where we have these low velocities here, approaching the class D-C boundary. Okay, after some much higher measurements, to the east. So that was kind of a surprise. No surprise in the by the sewer plant on the east side of the valley, the tertiary andesites, unit TA on the map, showed moderately high velocities, but still not hard rock velocities. Here's another product that you can get out of the refraction microtremor surveys. So at each of the 52 points, spaced at 300 meters, from west on the left to east on the right, we have the full velocity profile with the shear velocity color coded. So the harder the rock, the more blue or even purple it is, and the softer the rock, the more yellow or orange it is for the really soft rock. So over here in the Truckee Meadows, where the Steamboat Creek goes through, and the University Farms are really quite soft. There's also a couple of soft spots out near the Grand Sierra Resort. Downtown here, it's kind of moderate, not real hard, not real soft, sort of yellow and green. But another interesting thing here is you can see the depth to tertiary sandstone, which is averaging about 150 to 200 meters in this area. So we have relatively soft quaternary sediments in green and yellow, and orange, and below that in blue and purple we have harder tertiary sandstone. But there's quite a lot of variation in all this. Of course, this one note I want to make is that this transect is this cross section here is highly vertically exaggerated. It's actually more than 1,600 meters. It's actually 16 kilometers. Okay, sorry about that, and only half a kilometer deep, from 0 to 500 meters deep. So this is about 200 meters depth right here, and that's kind of a so it's that's why it looks so blocky. It's highly vertically exaggerated. Now, one thing we try to do is look at the correlation of our VS30 to the geologic map units and also to agricultural soil map units. And as has become typical, and I'll show you more examples. We plot the points in which are the pink points, and we have 52 on here, and 2 of them are distinct. These are the tertiary andesite. The unit names are down on the bottom of the scale here, and the tertiary andesite has an average that's just above 600 meters per second, and that is distinct. The average is the blue diamond, so there's blue here. You can see every other unit that has more than one measurement pretty much overlaps all the other units, of different kinds of Tahoe outwash, various kinds of alluvium and fluvial sediments. So very, very difficult to use shear velocity to separate out different units. Kind of makes sense. All these units have overlapping velocities, and what that means too is that you can't take a geologic map and just other than distinguishing tertiary bedrock from quaternary sediments. Period. You really can't draw any a velocity map from or a hazard or classification map, seismic classification map from a geological map. And the same with the soil units. All the soil units that have various all the soil units that occur in the agricultural maps. They really also have overlapping, highly overlapping velocities. One of our former students, Asha Pancha, was after some study, she was able to conclude that if you go beyond the soil unit and you actually, as assessed, it's just given on the agricultural map, and you actually assess grain sizes and other details of the soils, from soil studies and soil pits, then with average grain size and that sort of thing, with some real details, that are not on the maps, you can find some good correlations, but you need this incredible detail. Okay, so we like to put this together in a sort of holistic view. Here's a map of basin thickness, which maxes out at just over 1 kilometer at the intersection on the west side of town of West McCarran and Mayberry. Big gravity hole over here, and you're going to study how to get this kind of a basin gravity map in this class. And then and you can see the Reno Basin is divided up into some sub-basins, and so that's one of the pictures of the earthquake hazard. The more basin sediment there is, the more earthquake hazard there is. And here's a view of the basin modeled from the gravity. That's from a paper by Rob Abbott and myself from 2001. So we have this view of the basin along the transect, and we can see that the transect basically agrees with this view that the this thin layer of a quaternary sediment on top of the much thicker sandstone, tertiary sandstones, is what's really affecting the velocities we see in the refraction microtremor transect. So putting all that information together, we started to assess a total hazard map for Reno, based on our velocity transect, which is here called the bike path transect. Based on our gravity work, we could start to project out where we had observed high velocities on the transect, where we have lower velocities, like here just west of West McCarran. Interesting occurrence of low velocities. Kind of this north-south line, which runs really through downtown, okay, and maybe the location of a significant fault. So west of the fault, it's in general harder through downtown, and east of the fault it's basically softer until you get to the sewer plant out here. And this is following the work done in Los Angeles. This is an estimate of earthquake amplification that would occur in the Los Angeles area. The more yellow, the more amplification. And this work has been extended quite a lot. But it relies on having accurate velocities. You can see there's various geologic units and engineering units that are mapped out here and given different velocities. Okay, and the more yellow the velocity, the more yellow on the map, the higher the shaking hazard. The high shaking hazards come from deep basins in the Ventura Basin, which is a big oil basin, as well as the Los Angeles Basin, which is also deep enough to have oil. Those are very deep basins. And also from the geology, like here at Alamitos Bay, there's this yellow estuary, which has some very, very soft soils. So we wanted to assess this. This is the geologic map that went into that previous picture. And you can see in green blue for NIHRP B projected, based on the geologic map, and green for NIHRP C, yellow for NIHRP D, and pink for NIHRP E, more hazardous around the estuaries by Long Beach and the ports. What we wanted to do is we'd noticed from our work in Reno that we could not correlate the geologic map to the actual velocity measurements, and we couldn't do that in Reno. Can we do it in Los Angeles? So we put in this 60-kilometer long transect of 200 different ReMi refraction microtremor arrays, and we had to spend several days basically laying down instruments, and we found that easiest to do along a bike path. We weren't trying to avoid traffic. We were just trying to get a continuous path where we wouldn't have to, we wouldn't have the students who were doing the layouts fighting traffic, just to, having to run along heavily trafficked streets. So the bike path was basically just a safety feature, and we just spiked the geophones into cracks in the pavement, and followed the bike path for 60 kilometers. Very simple, a 300-meter long array of 15 sensors with their individual recorders in the foil bags. 20-meter takeout interval, and recorded for 30 minutes. And then we would pick the array and move it to the next spot. So with 3 different crews and 4 teams with 3 people each, it took only 4.5 days to profile the 200 different refraction microtremor arrays down this distance of 60 kilometers. There were some things we had to worry about. The bike path follows a levee of one of the rivers in the area called the San Gabriel River, and here's a test we did on another levee. We put an array right along at the top of the levee where we were going to be doing our survey, and then we put an array just off the levee, about 6 feet lower in elevation. And what we found is that if we adjusted for the different height, then the results laid over each other pretty closely. Okay, so and the VS30 especially was virtually identical between the 2 measurements. So really no issue with measuring on top of the levee. We're using very long wavelengths, low frequencies, and that we're just coming right through the levee. Okay, so here's the results from the San Gabriel Mountains in the north through the San Gabriel Valley on the left, and then past Whittier Narrows and into the Los Angeles Basin proper, and then down to Long Beach and Seal Beach on the right. Okay, measurements at Terminal Island over here in these symbols, but the main transect measurements in as the blue dots or black dots, and there were a number of other measurements taken away from the river course, just to do a test. Was there something unique about the river course? And that turned out not to be true. Certainly a lot of variation up near the mountains, and in these actually quite steep alluvial fans, very rocky, very bouldery alluvial fans. But in the Los Angeles Basin itself, really almost no variation, on or off the levees or near the river or not. A few anomalous points that maybe need some closer examination. But we found that basically, the shear velocity had been underestimated by the classification based on geology. The area up in here in Azusa, California, was so bouldery that it was higher velocity than was expected, and also, right through most of the Los Angeles Basin, we're really at the upper edge of the expected seismic hazard class, and then down in the south end, well, we were definitely right in the middle of the expected classification, except that estuary I talked about, the Alamitos Bay estuary. The measurements were not as low as were expected. You can see again they're at the top edge. Again, we tried correlating against geologic units. Okay, artificial fill maybe is noticeably lower in velocity, but otherwise these units are arranged from left to right by the recency of the sediment. Okay, and to the left is older sediment, and to the right is younger sediment. And surprise, surprise, unlike our original suspicions, we thought the youngest sediment would be the lowest velocity. Well, actually, the youngest sediment had higher velocity. Okay, and then if we had some areas that were a mixture of sediment and natural sediment and artificial fill, where the ReMi array crossed a boundary, we had similarly high velocities. In the middle of artificial fill, we certainly had the lower velocities. But again, really hard to correlate. Big ranges, and all the ranges are still overlapping. Same deal, maybe even worse with soil type. The more measurements we got in a particular soil type, just like making multiple measurements in a particular geologic unit, the wider the distribution of velocities that we got for that type. So, while there's a possibility that some soil types are, maybe have recognizable velocities, like this soil type 7, the Vista Amargosa Association, just not a lot to go on there. So let's take a look at what we did in Las Vegas. We took a route from this map on the left is the result of a number of experiments that were done in Las Vegas in the about 10 years ago. And the blue area are the deeper regions of the Las Vegas Basin. Las Vegas is underlain by a huge basin that gets almost 5 kilometers deep of tertiary sediment, tertiary and quaternary sediment, basically just west of Frenchman Mountain. It's the deepest spot. The Strip and downtown is along this area, and that was the area of our transect. Okay, here's a more close-up map. You can see where there are some faults. Some of the blue is deeper parts of the basin. The green is the shallower parts of the basin. Here's the stratosphere tower, and these green dots, which you can see in some places, show you where the center of uh, our combined arrays were. Again, we got about 50 arrays, and here they are arranged in terms of their in one of these 20 times vertically exaggerated cross sections. So it's 13 kilometers long and 300 meters deep. Okay, 20 times vertical exaggeration again. Where it's grayed out, that's where we kind of lost confidence in our ability to characterize the velocity. There's a certain depth for that in every survey, and you can see up north, where our work crossed these fault traces here. That's where we had the lowest velocities at the surface, and then some of the higher velocities are where we were on the strip and going past some of the bigger casinos. You can also see there's these isolated blue spots. Well, those are probably discontinuous layers of caliche, maybe fairly thick caliche, like 10 meters thick here, and that's the soil cementation by calcite that renders a lot of Las Vegas soils very high velocity and very hard to dig in. Here's an example of some of the data. The here are the pics on the PF plots. Okay, and a lot of it is fairly monochromatic in terms of velocity. Okay, so we have extremes of dispersion. Okay, and we use those to evaluate how much we believe the extremes of the velocities. Here's the VS30 results. Okay, again, north is on the left, and distance south. The Las Vegas Strip is in this area. The faults are in this area, so we have lower velocities near the faults, and higher velocities, in the areas along the strip that have more caliche. And what's particularly prominent here is the big variation. From place to place, there's a lot of variation in velocity in Las Vegas, and a lot of that has to do with that proportion of caliche. But really, total overlap versus VS30 versus the geologic map. Really, we cannot use a geologic map to really predict the VS30, and some indication that maybe one could predict VS30 on the basis of its agricultural soil type. There's these 5 units over here that show higher velocities. This one unit, which is everywhere and shows a huge range of velocity, but a few units that show lower velocities. So there was some hope. So we tried, and this is the agricultural soil map in black and white on the left, and there's our line of measurements. Okay, so we attempted to make some soil map correlations, and then we measured a couple more points and found that we measured a high velocity that appears here in blue, doesn't match what's predicted from the soil map around it, and over here we have the soil map predicts blue and green, and we get orange almost. Okay, so doing some sort of jackknife tests on this, very difficult to get accurate predictions. Here's another example of the failure of prediction. We use these stations in the center, these measurements in the center, along with the transect to predict, to essentially make the soil map. And then we measured 4 more sites. So according to the soil map, the 4 sites were all supposed to be between 700 and 800 meters per second VS30, shallow depth average shear velocity. And then when we actually measured those 4 sites, the velocities diverged. A couple of them turned out to be much lower. A couple of them turned out to be much higher. So not a great deal of predictive capability. Okay, so we had as well a number of well logs, and this is work done by my colleague Wanda Taylor, who at a couple of times had been head of the geology department down at UNLV, and so she looked at about 1,400 wells and compared, made a 3D model together with Jeff Wagner of Livermore Lab. They made a 3D model of the shallow sedimentary geology, all throughout Las Vegas Basin, from these wells, which are dense in some areas and not very dense in others. And then we looked at how that model intersected with our shear velocity measurements, and we predicted a map of VS30. Okay, and here the map is presented in two ways. It's presented, with orange being the lowest velocities, and green and purple being the higher velocities. And here it's presented in kind of hazard color scaling, with the more yellow being the more hazardous, the low velocities, and blue being less hazardous, the higher velocities. Okay. And this incredible level of detail is predicted from all those wells. So the well logs and the model, predicted the blue line here, and then our measured values are the red line. Not pretty good prediction. Okay, if you get enough data in there, you can actually do it. But we realized that to get a real map of earthquake hazard in Clark County, we were going to have to really do the job of measuring it. So we started the earthquake parcel mapping project in Las Vegas. We got started in that in 2007, and by the end of 2010, we had measured over 10,000 sites. Okay, here's a map of the with a purple dot at each of about 9,000 sites in Las Vegas Valley proper. You can see that we had to unfortunately miss almost all of the city of North Las Vegas. We got most of the city of Las Vegas proper, which is really just the north side. And the people who paid for this mapping were the city of Henderson and the county of Clark. So they, we made sure that we covered all developed and developing areas of the county and the developed areas of Henderson quite thoroughly. So there's an array here about an average of every 400 meters. Basically one array per or two arrays per 40-acre plot, if you want to, or parcel, if you want to put it that way. There was, a few areas that we had to miss, like the airport runways. We couldn't get measurements on because the airport's in use 24/7. So here's the eventual parcel map. The California-Nevada border is down here, and the town of Prim, right on the border, is down there. We made a lot of measurements, almost 1,000 measurements along the mapping out the I-15 corridor. Here's the measurements in Las Vegas Valley proper. There are also measurements in other areas like Laughlin and up in some of the developed areas north of Las Vegas. So quite a bit of data here, more than 10,000 measurements in all. And a couple of things that I could point out. The lowest velocity area, the Nehert D area, is rendered here in this map done by the county in blue. And you can see it's very hard to define the boundary of the most hazardous area. It's kind of like Swiss cheese. looking at the boundary between the NEHRP D blue area and the NEHRP C, the less hazardous green area. Okay, and actually that holds true for over most of it for the boundary between the much less hazardous, as I call C plus area, and the moderately hazardous green NEHRP C area. Okay, along the I-15 corridor, that's again like Swiss cheese. But on the west side of Las Vegas Valley, you can see 3 alluvial fans. Right, these are the toes of 3 alluvial fans, and easily see the bajadas in between. Right there and there. So really a spectacular correlation there. Shear velocity, at least in this area, correlates pretty closely with elevation and slope, but elsewhere not. It had to be measured to figure it out. Okay, so let me try to summarize what we can do with refraction microtremor now. All right, ReMi allows rapid seismic shaking hazard classification, and that's required by the International Building Code versions from 2000 to 2007. In fact, there's probably a 2012 IBC as well, and it still requires 30-meter depth shear velocity average for every single building project, and or in fact for certain mechanical things like having your plumber put an air conditioner on the roof. Okay, requires knowing the seismic shaking hazard classification, requires a soil measurement. Now, if you're lucky enough to live in Clark County, you can go to their website and you can look at their GIS system online, and you can find your property or the property you want to buy, and you can get a soil classification right there. So in Clark County, after the parcel mapping project, it's very, very easy. Okay, so you don't have to have your plumber wondering what your classification is, and overbuilding as a result of not knowing. In Clark County, Okay. Otherwise, you've got to measure it, and ReMi is the cheapest and most effective method of measuring seismic classification. We've also done a fair number of long transects of many ReMi measurements, and we've geophysically characterized the spatial variations in shaking hazard. Is it organized? Can you have any hope of predicting or matching? Seismic classification from and velocity. You have any hope of predicting that from a geologic map or a soil map or elevation or anything like that? There's only a few places where you can do that. Like the west side of Las Vegas Valley. Other places like central Las Vegas Valley, no hope. You got to measure it. Okay. So that's what I've just said. Map soil and geologic units can't reliably predict the measured VS30. So parcel mapping turned out to be necessary, and Clark County, stepped up to the plate, and they accomplished their parcel mapping before anybody else. So there are these places where our measurements suggest one can use river gradients, quaternary thickness, alluvial fan composition. So there are maybe a few places where you can predict shallow velocities, but basically, I feel that parcel mapping is going to be necessary for true seismic hazard mapping everywhere. You just need to check and see. So that's this is the end of lecture 2 in refraction microtremor, which talked not about the method itself, but more about its application. And with the work that we'll do on our field exercises, you'll be able to apply what you've seen here.